So now we're going to do a deep dive. We're going to first start with CVD, chemical vapor deposition.
So the first step of CVD growth is to prepare the seeds. Great care needs to be taken to minimize the number of imperfections in the seeds such that you get a high-quality diamond grown on a high-quality, well-prepared seed. The seeds are strategically laid out in a reactor. Gas is removed from the reactor and hydrocarbon is put into the reactor, and microwave energy breaks apart these hydrocarbon molecules such that atom by atom, the diamond grows vertically in that vacuum chamber. On the edges of these diamonds, you get what's called polycrystalline diamond material. That's the black rough you see around the diamond. You simply use a diamond cutting laser to remove that material, and then you can prepare that diamond as a cut and polished gemstone. Most CVD growers choose to post-growth treat their diamonds. GIA says about 80% of the diamonds they see today are post-growth treated. This is a simple process with which the diamond is placed within an HPHT press. It's about a 15 to 30 minute process to pressure cook that diamond to remove some of the voids, defects, and issues within that diamond, resulting in a higher quality, harder, and superior optical diamond. Since 2009, GIA has seen a steady increase in the proportion of CVD diamonds compared to HPHT diamonds, such that about 80% of the lab diamonds submitted to GIA today for lab diamond grading reports are in fact CVD diamonds. So why is CVD outpacing HPHT? First off, it's more efficient than HPHT, so it takes less electricity to grow a CVD diamond than an HPHT diamond. It's a smaller physical footprint. The CVD reactors are about the size of a regular refrigerator, not a 70-ton device the size of a bus. It produces type 2A diamonds that test as diamonds on diamond testers, does not test as moissanite. That are completely inert typically under shortwave and longwave fluorescent light. And lastly, it's an observable process. So through a window, you can watch CVD diamonds being grown. If there's an issue, you can stop the process, fix the issue, and restart.
So what are the drawbacks and limitations of CVD? Well, it's slow. It requires expensive seeds, typically from third parties. We'll get to that later. That's a big one. It's certainly more prone to material issues like strain, blurriness in the crystal, and it's not suitable for melee. So melee are the small accent diamonds that are used in jewelry. Typically, melee and lab grown is HPHT grown, and it's almost entirely DEF color and high clarity. If you were to pair bright white colorless accent diamonds with a much warmer color tinge, a CVD diamond, sometimes the color difference between those two can be noticeable. So let's get into some color tinge issues in CVD. In this video, every single one of these was a certified G color, but you can see that there's obvious differences in the color tinges. So we're going to now jump into the first of our BGS letters. That's B is for brown. And brown can be more of a pinkish brown, like the one you see on the left, or it can be more of a grayish brown, like the one you see on the right. And it's worth noting, both of these diamonds came from the same grower. Brown tinge does occur in natural diamonds, but the reasons for it are completely different and typically at different levels.
So in CVD diamonds, the brown is caused by two things. Empty voids within the diamond's lattice and nitrogen atoms trapped within the crystal. Nitrogen can occur in CVD diamonds in two ways. It can be an accident. It can be something that leaks past the seals, like through the gaps of the vacuum reactor. Or it can be something that's intentionally added. So when you add nitrogen to a CVD reactor, you can grow diamonds 200, 300% faster. But the faster you grow a CVD diamond, the more risk there is that something goes wrong. So as the carbon atoms are stacking and stacking and stacking, you can have faults in that. And those faults manifest themselves as what's called a void in the crystal structure. So here's an atomic level look at a void. What we've done is modeled it and then cut the void in half and then made that cut line in green to make it quite visible. So it's literally an empty spot within the crystal where there are no carbon atoms or other atoms in that crystal. And when light passes through voids in diamonds, you get a brown tinge as a result. Going back to nitrogen, nitrogen can also give CVD diamonds a brown hue. Even though there's a far lower concentration of nitrogen in a CVD diamond than a natural diamond, you still get a brown hue or tinge because the nitrogen is not aggregating, and that's more optically active when it's a single substitution of a nitrogen atom than when it's multiple nitrogen atoms joined together. If that nitrogen atom is next to a vacancy within the crystal structure, you get a slightly different type of brown. So this is called a nitrogen vacancy defect, and you get a pinkish brown rather than a true brown. So going back and forth, if you look at the diamond on the right, this is a sort of true brown from nitrogen defects, whereas it's slightly pinker if there's vacancies associated with that nitrogen.
If the color of an as-grown CVD is brown, it can be made colorless through post-growth treatment, which we'll talk a little bit more about later. That treatment effectively can remove the voids from the crystal structure and aggregate those nitrogen atoms. So if it's a little bit hard to see in this 360 video here, you can see the untreated has a bit of a brownish tinge. But if this video is a little too difficult to view on this monitor, here's an extreme example where you have the before treatment on the left, and then you have the after treatment on the right. The second letter of our BGS is G for gray. And gray is the most prevalent color tinge in CVD. It's fairly challenging to spot in 360 videos, so it's also the most concerning. And it has a lot of reasons for why it happens. In this example on my hand, both of these pear-shaped diamonds received an F color grade. The one on the right has a more prominent gray tinge. Here's another example. The diamond on the right has a more prominent gray tinge. Both of these are GIA certified F colors. And this can be seen all the way up to D color. The diamond on the left has a more prominent gray tinge than the diamond on the right. But to be clear, obviously, the higher we go up in color or the less present of color, the less obvious color tinges are.
So there are a number of reasons that CVD diamonds can be gray. The first is silicon trapped within the crystal structure. So silicon is a much larger atom than carbon, and so when silicon gets stuck in the lattice, you have two voids on both sides of the silicon. The source of silicon within CVD diamonds is often the windows, the quartz viewports with which you view the reaction. The plasma, the same plasma that's breaking apart the hydrocarbon gases, is ripping silicon off the inside of this window, and that's getting trapped within the diamond. And silicon is very rare within natural diamonds. The second is an overcompensation of boron. As we discussed earlier, you can dope your diamonds with nitrogen and grow them much faster. That gives you brown diamonds. Well, you can then add boron on top of the nitrogen to balance out that and remove the brown. But if you add too much boron, you get grayish diamonds. This is something that GIA was not observing 2 years ago, but they're now increasingly seeing it in CVD diamonds submitted for grading today. The third is graphitic or graphite nanoclusters within the diamond. The reaction of growing CVD diamonds is quite a chaotic process, and sometimes those carbon atoms, as they attach to the diamond, they don't actually attach as diamond, but instead as graphite. And so trapped within the massive crystal of diamonds, you can have little tiny microscopic pieces of graphite that then cause a grayish tone to the diamond. Gray, unlike brown, gray gets worse with treatment. So this is a model of a void again, but in this case we have a small piece of graphite that we've represented on the side of the void. So this void gives you a brownish tone. You then post-growth treat this diamond to collapse that void, to make that void disappear. But in the process of doing that, the amount of graphite actually increases. So every time you heat a diamond up, you can't get the graphite out of the diamond, or it's very, very difficult to get the graphite out of the diamond. Instead, the graphitic inclusions increase in size as part of the treatment process. So easy to get brown out, extraordinarily difficult to get gray out of a diamond.
So gray is the most common color tinge, as I mentioned, and it has multiple reasons that we'll recap. So if you run your machine too aggressively, it can essentially have the plasma melt the quartz viewing window, which creates silicon defects or silicon vacancy defects. That leads to gray tinge. You can run your machine with catalysts, such as adding nitrogen and then perhaps compensating boron, and then that certainly can produce a brown tinge, and then you end up with the gray tinge from the boron. You can also just grow it too fast in imperfect conditions, as Jason mentioned. You can end up with graphitic nano-inclusions. Then during the treatment process, those graphitic inclusions collapse the void and expand, leading to a gray tinge. So the takeaway is that everything you're seeing on the left side are all attempts to grow faster for lower cost, and the things on the right side are the consequences, aka the gray tinge. So the next topic that we're going to cover in BGS is strain.
So strain presents as blurriness in the crystal, almost like streaks of Windex, like something you can't fully ever get the diamond clean. And it's similar to graining in natural diamonds, but more dispersed throughout the crystal structure. Here's a look at a rough CVD diamond where the strain may be more visible to you. So without the faceting, you can see that in the layers you have a scattering of light as the light is hitting those dislocations and areas of strain within the CVD crystal.
So strain is not measured as a binary, but rather exists on a scale of good to bad. There's little to no consensus in the industry as to what is negligible, light, medium, and strong. I just made this up. Based on my own opinion.
And strain is not a clarity setting feature. So this doesn't appear in inclusion maps, it doesn't change clarity grades, but it does change the light performance of a diamond.
And these are all VVS1. So crystal strain looks very different in different types of diamonds. Here we can see a cross-polar filter for natural, as-grown CVD, treated CVD, and as you can see in HPHT, almost no strain. It's characteristic of HPHT. That's another good example of how it is not possible to evade detection or fool testing equipment.
So how and why does strain appear in a CVD diamond? Well, it starts with the diamond seeds. So there's no such thing as a perfect diamond. There's no such thing as a perfect diamond seed. Every seed, no matter how high of purity, will have thousands of issues, dislocations, or problems within the seed. So here's an X-ray view of a diamond seed. So you can see stacking faults appearing on various edges of the diamond. And when you grow in the CVD reaction on top of the seed, everywhere that there is a defect or a problem in the seed crystal, you'll get bundles of dislocations that rise out of that point, which result in that blurriness that we've just shown. And the seed quality defines the diamond quality. So here are a couple of examples of diamonds for sale on LinkedIn, and the quality of these diamonds is very different, and that's based on the characteristics of the seed. So for example here, this stone here that's relatively clear might yield a beautiful colorless diamond, whereas this one here might be a blurry, brownish, unexceptional diamond. So here's another example of how this manifests. So these are X-rays of CVD-grown diamonds that show the difference in the number of faults in the diamond based on the quality of the seed. So on the left here, I have a relatively high-quality seed that has one major bundle of dislocations, and progressively worse seeds that have more and more dislocations in the crystal as a result. So this is how it manifests, where those same three diamonds I just showed you, this diamond is very opaque, high quality, has high optical transmission, progressively worse to this diamond being something that will be blurry, unexceptional, and uninteresting to study. In addition, seeds deteriorate with use. So every time you use a seed, every time you start and stop your CVD reactor, the quality of the seeds decays. Using the laser to cut the grown diamond off the seed can cause issues. And so you recycle these seeds and they get poor quality each time. It's extraordinarily expensive to procure good seeds, and so it's a difficult challenge for the CVD industry.
HPHT treatment heals strain, simply put. So you can see on the left, this is untreated as grown CVD, and on the right is treated CVD.
So the strain within diamonds accumulates as the diamond grows until that strain boils over into polycrystalline diamonds. So it's similar to twinning in natural diamonds, but a slightly different phenomenon in CVD diamonds that results in little brown inclusions or clusters within the diamond. So here on the left, I have a CVD diamond that has polycrystalline throughout the diamond, whereas on the right, we have an HPHT diamond.
These received the same clarity grade of I1.
So here's looking at that process through a microscope. So each of these black dots in the center of a diamond here are those polycrystalline nodules within the diamond, and they're occurring as the strain increases in the diamond. So if you're growing diamonds, you're looking through that quartz window, and you see those little black granules appear. What do?
Well, you stop your reactor, you take the diamond out, you polish off the polycrystalline, and you put it back in. And this causes the next part of our BGS, and that's striations. This is the impact of starting and stopping the CVD reactor. Now, to be clear, nearly every CVD diamond has some level of striation rings, some level of starting and stopping. It's not a binary. It's measured on a scale of how many. And not only that, but how closely together these start and stop growth cycles occur. So you can see here on the left, we have a diamond view of a diamond with 8 growth cycles, and you can see it's represented by rings, almost like rings on a tree. And you can see that some of these are fairly close together, right? Meaning that those growth cycles didn't go for very long. Then a nice long gap, and then started and stopped again. And we actually have this diamond here with us today. One of the things that's interesting to note about striations is the way it presents to the naked eye. So you can see on the right here is an example of a stone that we assume has several growth cycles. The best way we can describe it is that it literally looks out of focus. Because of the way that the light is scattered in the stone as it hits these various growth rings, the diamond looks like, well, it's just never going to be in focus. Again, this might be a little hard to see on this screen, but the diamond on the bottom is the one that has 8 growth cycles. And you can see it's just kind of dead, kind of lackluster, lifeless, versus the diamond on the top has a lot more contrast. You can really clearly see into it. It's got a more transparent material. That's really the difference between heavy striations and not. This is another striation case study that we did. It's a little hard to see, but if you were to look at the image here in the center, there's literally visible growth rings that you can see. They're gray. And they're visible under 10x magnification. Here it is in the diamond view. You can see the more obvious growth rings along here. And what's interesting about this is that, as far as we know, striation rings do not contribute to clarity grade.
So how do those rings form? Why is it that in a diamond view we see discretely different colors at those junctures? The answer is that the conditions when you start a CVD reactor are very different than the conditions when it's running at steady state, everything's working correctly. So here's a photoluminescence look at a table of a diamond where we have 2 start-stop striations. We've got one here and one here. And they found that the concentration of silicon in the diamond was radically different after the diamond was restarted. So this dark blue area, things are running well, plasma as well. You restart it, you have significant inclusion intake of silicon in the diamond, which then decays back to a high quality diamond. As we discussed earlier, silicon can make diamonds gray. So this diamond here will have gray performance when looking at it table up.
So here's another case study diamond we have. It had a pinkish gray tinge in person that we were really curious about. And we sent it to GIA researchers to get their thoughts on it. In spectral analysis, it showed unusually high silicon and silicon vacancy defects to the point where we concluded that this level of silicon was likely not from etching off of a viewing window, but was likely due to doping, likely due to silicon being intentionally added into a reactor. You'll also notice the very clear, distinct growth line there, and then the way that the diamond looks on the left and right, indicating just completely different growth sectors within this CVD diamond. And really what we conclude likely happened here is that this diamond started in one reactor, was then removed and put into a different generation reactor, possibly one that was being used for research and development purposes. And that is the culprit or the cause of the amount of silicon concentration. It has a very uniquely ugly gray color, and it's really cool. So if you want to see it, we have it here.
So 80% of diamonds, CVD diamonds inspected by GIA have post-growth treatment. Why? Proper HPHT treatment improves the quality of a CVD diamond.
We think that the resistance to post-growth treatment is probably a hangover effect from the natural diamond market, where introducing a man-made concept like treatment onto a natural diamond and not disclosing it is problematic. But we contend that in lab-grown, it's a man-made process throughout the beginning to the end. What one entity says is treatment, another might say, oh, that's just diamond growth. Untreated CVD has flaws. It's not as durable. It can have crystal material issues, can have brown. But not all treated CVD is good, and not all treated CVD is bad.